Okay, hi guys, my name is Ryan Moscoso. I'm the team lead for concussive forces in competitive sports, the research team here. We're working under Dr. David Rankensmeyer and Dr. James Hicks, looking into the sports of water polo and soccer to see what a distribution of pressures and velocities does to impact forces. I'd like to introduce our team real quick. I'm Wyatt. Like I said, team lead, and I'm also in charge of data acquisition. This is Tyler. He does ball requirements and data input, also a part of our data acquisition. Jordan is our measurement and forces. He also does our speed calibrations, equipment setup, radar gun. And this is Sherry. She's our documentation. We have 4 people in our group, much smaller than most of the design groups out there. And so this breakdown of our team is actually pretty accurate to exactly what we do, and we don't really need a more detailed breakdown because we have such a narrow focus for each of us and we know exactly what we're doing. So I'm going to hand it over to Jordan here.
Okay, yeah, so concussions. There's a lot of talk about concussions going on right now. It's a popular area, and it's the most common type of traumatic brain injury. So what is a concussion? It's common, and it's kind of difficult to specify. I come up with a specific definition for it, but in general, it's a type of traumatic brain injury in which there's a severe head impact. So your brain and your skull are coming in contact, and the fluid in there is moving around, and you're having memory loss, headaches. So there's a lot of different types of balance, concentration, things are affected. And so there has been a lot of research conducted in some of the more contact-heavy sports, such as football, but in sports like soccer and water polo, there is hardly anything. And so that's kind of the incentive here is that this is kind of a new territory, and we're interested in finding out what kind of forces exist in those sports. And it is a relevant issue because there are a lot of head injuries in these sports. You can see there are about 24,000 cases of soccer head injury in 2009, about 28,000 cases of water sport-related injuries in 2009. So these injuries are occurring, and we're trying to come up with some research to address the issues and find out potential solutions. And the reason we chose soccer and water polo is, like I said, there's not very much information out there about it right now, but also soccer is one of the only sports that condones active heading. So, active head contact is part of the sport. And water polo is one of the only sports in which the ball is traveling the same plane as the head, so there's just naturally going to be a lot more contact with the ball. So that's kind of why we chose those 2 sports in particular. And then this is a little more incentive. I'm just going to read this quote here from the NCAA. The rule recommended by the NCAA Men's and Women's Water Polo Subcommittee prohibits the use of padded caps, which are becoming more popular among water polo players concerned about concussions. The committee bases its decision on the fact that, according to the NCAA Sports Science Institute, no scientific evidence supports the notation that padded headgear helps prevent concussions. So part of our experiment is also looking into this aspect of it. Does padded headgear actually help reduce your risk of getting a concussion? Does it reduce the impact forces significantly? So just to review what we did last quarter, a lot of research into what's already out there. Like I said, there wasn't very much. We found a couple studies that gave us some good information, but it was just a lot of research looking into the science behind concussions. And then we started to set up our experimental procedure. We started to figure out how we're going to test this, what the specifications are going to be, how we're going to acquire the materials that we need for testing. And it was also a lot of financial proposals and getting the funds that we need in order to carry on with experimentation this quarter. And that's what it is. So I'm going to hand it over to Wyatt now, who's going to talk to you about the costs and some of the materials that we're using.
Okay, so our financial proposal to Dr. Hicks involved various things. The main mode of us measuring these forces is going to be an anthropomorphic testing dummy. This anthropomorphic testing dummy we actually rented from Humanetics, and you can see it on the next slide. It can be full length, totally head to toe a human, but we're actually just renting the head and neck, and that's $35.64 for just 1 week, fully outfitted with 3 internal linear and Devco piezo-resistive accelerometers and 3 internal DTS-ARS angular rate sensors. These 2 accelerometers will give us the 6-axis force distribution and data collection that we need. additional things were our digital gauge. Obviously, since pressure is the main focus of our experiment, we want to get this pressure distribution. We need to have an accurate way of measuring pressure. We have a velocity speed gun, soccer balls, water polo balls, and finally, new accelerometers, which recently was the main expense, because when we received the equipment, the accelerometers we had actually weren't calibrated correctly. They were extremely insensitive to impact, and they required not only a high-pass filter, but amplification to them. So we got those devices, outfitted the dummy with it, and now we're ready to roll with our experiment. The anthropomorphic testing dummy, this is just an outline of what it is. It's a 50th percentile hybrid male dummy. It has excellent biofidelity, so it mirrors what my head and neck does whenever I get hit with a ball, the good damping, good surface friction and stuff. And it has very good outfitability or capability for instrumentation. It has spaces for a 6-axis load cell on top of the 6 accelerometers that we're already using, but for our purposes we're just using the 6 accelerometers. And now I'm going to hand it over to Tyler.
So as Wyatt has already said, Jordan kind of talked about, just to reiterate, our primary project goal is to ascertain whether ball inflation pressures and velocities have a huge impact on traumatic brain injuries and the accelerations felt by the head and the brain. Auxiliary project goals include comparing the data collected that we have, because these sensors are very precise. There's a few groups that are part of the concussion research here at UCI that are using, along with the soccer team, these G-Force accelerometers. That's the name of the company. So they actually asked us to compare our results as well as having one on our dummy to see what kind of precision those have. As Jordan talked about, we are researching whether the padded headgears in the market actually reduce the force felt by the head. The Cap 7 company claims that it has a 30% force reduction. We are finding, we'll be talking about our data in a little bit, we're almost there, we're finding about a 20% right now. And potential goals would be to try to redesign or help give modifications, ideas to help these headgears and possibly redesign one for ourselves. This is a little timeline for us. As far as looking at last quarter was the project start, project details. Currently we're in this middle section, impact testing, data acquisition. We've been doing it this entire week. We've been out on the soccer field about 8 to 10 hours a day, just hitting the dummy head with balls. And we're going to see a picture here in a second. Our turnaround for each run is about 3 minutes, so we're pretty good at streamlining it now, and it's moving a lot quicker. Next will be data analysis, thesis reporting, and the year will be over. So when we talk about the experimental procedure, every time that we go out there, we have about 30 minutes set up. I actually want to go to the next slide real quick. Wyatt's going to talk about this, but this picture I really like. So here on the left, we have the ball launcher that we're using from the soccer team. The radar gun is actually tucked just behind that. We're keeping that constant on a tripod in the same spot every time. We have our head that's mounted to a steel bench that we drilled into. We insert that, and then that has the goalie headgear on it. So every day that we get out there, we have to set this up. We have the radar gun displayed for the person sitting on the bench to be able to keep those constants too, or as well. Once we get there, we plug in the ATD. The software that we have actually lets us see an oscilloscope of the head. So we actually go out there with a hammer, hit it on each axis, make sure that we're getting a good signal back, and then we go into testing. And then we calibrate our ball launcher, get our right speed, check our pressures, and get going. I'll talk more about the experimentation.
Okay. So the biggest part of this was our data acquisition system. It's kind of the most important thing in terms of getting an accurate feel of what's going on, because of all the noise associated with electronic equipment. That was the main thing that we had to deal with, was that, as I discussed before, the accelerometers were way too low in calibration, so that the noise actually ate up the entire signal it was reading. So a big part was filtering the signal, amplifying it to something that we can actually see. And for our actual experiment, the ranges that we're going over for water polo, since the average ball pressure is around 13 to 14 psi in professional matches, we added one to each end. We do 12, 13, 14, 15. And then we added 2 more on the other sides of the spectrum just to get a feel for exactly what pressure is doing on a larger scale. So we do 10, 12, 13, 14, 15, 17. Then for soccer, we have a similar scenario. We have 5, 7, 8, 9, 11, because it's from 7 to 9 that the average player will be playing with the soccer ball. For our velocity measurements, and that's also why we have our radar gun, we go from 35 to 55 miles an hour. We're going by 5s, and we have 12 trials for each speed that we're going at and each velocity. So we'll do 6 trials for having no headgear on and 6 trials with having headgear on. See what the difference is in terms of the G-force, which is what's output into our data acquisition system and readily available on our computer. And then we move on to the next speed with the constant PSI, constant everything else. So after the past week of testing and the deliberation, after plotting it on Excel and stuff, we came out with these results. So the way that these results are, we have, like I said, 6 trials for without head, 6 trials with head. So these are just the 6 trials without head, just as a comparison. So we have 6 trials at 10, 12, 13, 14, 15, and 17. If you notice, it's basically a general upward trend from about 35 at 10 to 37, 38, 39, 39.5, and then hitting over 40 at about 41 at 17. So we're getting kind of what we expected from our data, and we're really happy to see it. This is a little easier to look at. This is the comparison between the 6 trials average for each point without headgear and 6 trials average for each point with headgear, to see the difference of what does headgear do. Because CAP 7 claims that headgear reduces forces by 30%. It seems a little bit of a stretch to have headgear do that much, so we're checking it. And if you notice, we have difference of 5, difference of 10, difference of 9, 8, 5, and 7 or 8. So an average of 8 difference, and around 35 to 40. So we're getting about a 20% reduction in forces just by putting on the headgear, which I personally did not expect. I thought they were kind of full of it, but it turns out their headgear really is reducing the forces, and it's largely because they're using an insulation layer of air. So they have the spongy pads which redirect forces and air on top of their existing headgear, gives it kind of the idea of, well, also in 151, the hot cups of coffee, they have air insulation to reduce heat transfer. So now I'll hand it back over to Jordan.
Oh yeah, so just kind of to recap what we've done so far this quarter. We leased the ATD, we got all the equipment that we needed, and all the materials, and then we began to set our experiment up on the soccer field, and we had to go through, like what I said, a lot of technical fixes with the accelerometers and with the data acquisition system. So we've gone through all of that, and now we're full swing into testing. We're almost halfway through our testing, and it will continue in the next week. And so that's kind of our progress so far in the quarter, and Tyler's going to tell you what we're looking at doing in the following weeks.
So our next steps will obviously be to finish the experimentation. Now this picture was actually taken by a girl in the, the student?
Office of Academic Initiatives.
Office of Academic Initiatives. She's going to write some stories on this for the website and to show where the money's going for the academic initiatives. Finish experimentation. We're going to try to streamline the data. That plot that you guys just saw was raw data that we just did this morning because we got most of our experimentation done in the past 2 days. So we really don't know what to expect as we get higher in our velocities, but we're going to assume it's going to be about the same. Like we talked about, being able to analyze these G-force trackers, try to help the other groups doing concussion studies here. That's what they've asked us to help them with. And then we're going to obviously write a report. This is why it's senior thesis, so it's going to be a pretty in-depth thing for us. And as well as we talked about the possible design of headgear. So that concludes it. Is there any questions at all?